Hi, I'm Ridula. This is Physics 2111 Lab, Experiment 4 Oscillations. The purpose of this lab video is to investigate the oscillations of a spring mass system, to track the observed position using a tracker and compare it with the predicted position in a computational model, which is ClosScript. A preview of the main result is that the energy principle is conserved as the change in total energy is zero, so the motion of the spring mass system can be predicted. The principles used in this lab video are Newton's second law of motion, which states that the net force is equal to the change in momentum of a body over time. So the net force for this experiment is the spring force plus the gravitational force. I also use the energy principle, which is the change in energy is the sum of work done by the surroundings and the thermal energy exchanged with the surroundings. So delta E of the system is equal to the work done by the surroundings plus Q. So here delta E of the system is zero, as the system is mass, spring, and earth, and the surroundings is nothing. So the change in kinetic energy plus the change in potential energy of the spring plus the change in gravitational potential energy is equated to zero. And I also use the velocity and position update formulas. The experimental setup. So the system is the spring, mass, and earth. The surroundings is nothing. The initial conditions are the initial position is negative 0.026 in the x direction and negative 0.959 in the y direction. The initial velocity is zero. The mass of the object oscillating is 0.402 kgs. So here I use the tracker to track each frame of the oscillating object. So on the right hand side are the x and y graphs of the object oscillating in the x and y direction. So to calculate the time period of one cycle, I found three different time periods in the y graph, and I took the average, which came out to be 1.54 seconds. And to find the spring stiffness Ks, I used the formula 4 pi square times mass divided by the time, which came out to be 6.52 Newton per meter. And to find the relaxed length, LO, I used the spring constant formula, and the answer was 0.125 meters. So this is my code in ClosScript, and these are the initial conditions. So there's gravity, and then the spring constant and relaxed length, which I found using my tracker data, and then L hat S for the spring formula. And then the energies, there's kinetic energy, which is half mv squared, and then the gravitational potential energy, which is mass of the ball times gravity times the position, and then the potential energy due to the spring. And then the total energy E is equal to the kinetic energy plus the gravitational potential energy plus the potential energy due to the spring. So this is the iteration loop where I'm calculating the change in energy for each time step. So I calculated the force of gravity, the force of spring, and then I found the net force. So with the net force, I can update the velocity and position with the velocity and position update formula. So once I find the updated velocity and position for each time step, I can use that to calculate the energies. So that's what I did in the bottom half of the code. So the kinetic energy, I calculated the change in kinetic energy, delta K, and then similarly delta UG for gravity, and then delta US for the spring, and then E is equal to K plus UG plus US, and then delta E, which is the change in energy, is final energy minus the initial energy. These are the model comparisons between the computational model and the experimental data. So they represent the oscillations in the x and y direction. So as you can see, for the model and experiment, they start off overlapping, but as time progresses, they tend to deviate, which are due to the sources of error. So there are two sources of error. So first is the tracking error. So when I manually tracked each frame of the oscillation, the placement of the point of mass may not have always been at the center of mass. And second, the work is done from the surroundings, as the system is not completely isolated. This is the energy graph where the change in energy delta E is zero, and delta U graph and delta U spring oscillate at a similar rate, and delta K, which is the kinetic energy, oscillates at twice the rate. So the first question is the energy principle satisfied? So yes, for my model, the energy principle is satisfied as the orange line, which is delta E, the change in energy, is equal to 0. So here I'm comparing both the oscillation periods. So in X and Y direction, I took the average of 3 consecutive time periods by looking at the X and Y graphs. And for X direction, I got 1.6. For Y direction, I got 1.5, which gave me 2 different spin constants in both the directions. So the reason for this is that different directions produce deviation in the time period that affects the spin constant.